So this is the instantaneous Poynting vector. It's 1 over mu naught times the electric field crossed into the magnetic field. And it will give us the direction the electromagnetic wave is traveling, and the direction in which the energy is being transported. So its direction points the way the energy is flowing, the way the wave is traveling. But notice this is an instantaneous energy. A lot of times we're not interested in the instantaneous energy. Remember, for optical wavelengths, this will cycle over 10 to the 14 times in a single second. Sometimes we're more interested in taking that energy per time per area, or power per unit area, and averaging it over time. So that's what this bracket here means. We're going to take the average over time. When we do that, the average of the Poynting vector is what's known as the intensity. And that's just the average power per unit area that we have hitting us at a given moment in time. For example, near the Earth's surface, the intensity of light from the sun is about 1,000 watts per meter squared. Now we can take this formula for the intensity and combine it with this formula for the Poynting vector. So let's take a look at that. We know the Poynting vector is 1 over mu naught c times the electric field squared, but to make it intensity, we take a time average. Well, the time average of the electric field squared is just the RMS value squared, because the definition of RMS is to square it, take an average, and then take the square root. We can combine this relationship for the intensity with the relationship back here for the Poynting vector in terms of the electric field, and we can find an average of the electric field in terms of the average intensity that we're experiencing. So let's do that. We know that S, at least in magnitude, is 1 over mu naught c times the electric field squared. But now if we average that over time, this becomes the intensity, and this becomes the average of the electric field squared. Now I can solve for that electric field, and I find that, darn it. Now, there's a special name for this way of taking an average. If I take the square root of that, then I have a certain kind of average of the electric field, which is the square root of the average of the electric field squared. So first we square it, then we take the average, and then we take the square root. What it's called is the root mean square, which stands for the root, square root, of the mean or average of the square. And it's a good way of finding averages for something like a vector electric field, which, if I just averaged it directly, would average out to 0. So this is the relationship we have between the intensity and the average electric field. The intensity is 1 over c mu naught times the RMS value of the electric field squared.